Many things can cause an electronic component on a circuit board to fail. Sometimes the component is defective. Occasionally, the soldered connections are made incorrectly. But a lot of the time, component failures are due to improper component identification, meaning the wrong component is mistakenly attached to the circuit board, or the right component is attached with an improper orientation. Knowing how to accurately identify components is critical for people working in the electronics assembly industry. This video training program will examine the various types of through-hole and surface mount components you'll be encountering. Through-hole components have leads that are designed to be inserted through mounting holes in the circuit board. Leads are rigid metal wires that extend out from the component. Through-hole components may have axial leads, also referred to as arms, or radial leads, also called legs. Surface mount components are designed to be placed directly onto lands that serve as mounting points on the surface of the board. They come in a variety of leaded and leadless packages. Let's begin by looking at some basic information about components. Components are devices that control the flow of electricity, so that an electronic product can do what it's designed to do. The most important components are semiconductors and are called active components. Semiconductors consist of both conductors and insulators. A conductor is a metal or material that will allow electricity to flow through it. An insulator is any material that has a high resistance to the flow of electrical current. Some components are active, meaning they can amplify or interpret a signal. Active components include diodes, transistors, and integrated circuits, also known as ICs. Other components are passive, meaning they cannot change an electrical signal, except to reduce it in size or delay it. An example of a passive component is a capacitor. When a component is packaged with only one or two functional elements, it is called a discrete component. An example of a discrete component is a resistor that performs the simple function of limiting the electrical current that flows through it. On the other hand, an IC is a group of interconnected elements assembled into a single package that performs multiple functions. A well-known example of a complex IC is the microprocessor found in computers. At this point, let's examine some of the important factors you'll need to be aware of to begin identifying and understanding components. We'll start with component marking. Every manufacturer of electronic components uses a slightly different system for marking components. This marking will either be on the component or on the component packaging. Typically, this information includes the manufacturer's name or logo, the component part number or ordering code, the lot code, the date code, and the country where it was manufactured. For example, let's look at the marking on this ball grid array from Freescale Semiconductors. As you can see, the logo is clearly marked on the component. The part number is MPC8270. If you were to search that number on the internet, you'd learn that this component is an integrated communications processor. The letter C refers to the temperature range, and ZU refers to the package type. The letters UPE refer to the processor speed. The last letter on the first line is the revision level of the die or chip. The second line specifies the 3 frequency rates of the processor. The third line is very important to understand because it contains the lot code and the date code. These codes allow us to track the manufacturing information for the product in the event a particular component has a problem and needs to be recalled. In this case, QQ tells us where these chips were fabricated and assembled. Q is the code for the Freescale manufacturing facility in Kuala Lumpur, Malaysia. The letters KZ specify the lot number. The last 4 digits tell us the year and work week that the component was manufactured. The last important marking is underneath the lot and date code and tells us that the device was manufactured in Malaysia. You don't really need to know all the details related to component marking, but this information is available in case the source of a problem needs to be identified. Now let's take a look at documentation. Every circuit board assembly comes with documentation that includes a bill of materials and an assembly drawing. The bill of materials defines all of the components used in the assembly by manufacturer and part number, or using an internal company part number. The bill of materials may also reference the type of component, its size, value, voltage, wattage, and composition. In addition, there is a component reference designator, or CRD, assigned to each component on the circuit board. For example, resistors utilize the letter R as a reference designator. If a circuit board contains 30 resistors, they are usually identified as R1 through R30, even if they all have the same part number or value. You can see the importance of reference designators when we look at the actual assembly drawing. This drawing shows the components and their location on the circuit board. The C designations on the drawing usually refer to capacitors, and the U designations usually refer to ICs. We'll discuss reference designators in more detail when we address the individual components. The important thing to remember is that the assembly drawing shows the location of the component by CRD. The bill of materials relates the CRD to a specific component part number. In addition, the component side of the circuit board is usually silk-screened with the identical markings from the assembly drawing. This makes the component identification and insertion process more clear. Another method of identifying some components is by their value. A value is a numerical quantity given to the component. This value is usually assigned a plus and minus tolerance, which is the variation allowed from that value. For example, resistor values are units of resistance measured in ohms. If a 250 ohm resistor has a 5% tolerance, its acceptable operating range would be 237.5 to 262.5 ohms. We'll talk more about specific component values and tolerances later in this video. Now that you see how the bill of materials and assembly drawing are used to properly identify the components and their locations on the circuit board, let's examine another important topic in component identification: the direction or orientation in which the component needs to be installed. Some components have both a positive and negative connection to the circuit board, and the leads must be inserted into the positive and negative holes identified on the circuit board and assembly drawing. Components with this positive and negative connection have what is called polarity. This works the same way as the positive and negative terminals on a battery. For example, a flashlight battery has to be inserted with the terminals in the right position for the flashlight to work. For components that have polarity, the positive lead is called the anode and the negative lead is called the cathode. The symbol for the positive anode is the plus sign, and the symbol for the negative cathode is the minus sign. A plus or minus sign is usually marked on the component, as well as on the assembly drawing, and on the component side of the circuit board. The direction in which a component is installed is also important for components with multiple leads, even if they do not have polarity. Proper orientation means that pin 1 of the component is in the same position as the pin 1 hole on the circuit board. The board usually has a square pad or a symbol or screened outline of the component shape to show the correct orientation. IC manufacturers use a variety of methods to identify pin 1 on the component package. Markings may include a notch, a wedge, a dimple, a different edge or corner shape, a stripe, or the actual number. When viewed from above, If the mark is at the top of the component, pin 1 is always to the left. The numbering of the other pins always proceeds in a counterclockwise direction around the component. When a component is not oriented correctly, the assembly won't function as intended and will fail electrical tests. When a component is inserted with polarities reversed, the component can actually be destroyed. There may also be damage to the circuit board. The result can be costly repair work or even a scrapped assembly. Now let's take a look at the different types of through-hole ICs. Remember, an IC is a group of interconnected elements assembled into a single package. Common IC packages include single inline packages, or SIPs, dual inline packages, or DIPs, IC cans, and pin grid arrays, or PGAs. SIPs consist of a single row of leads and are often resistor networks or diode arrays. The reference designator for a particular SIP is based on the function. Resistor networks will usually use R for a reference designator, and diode arrays will use a D or CR. In many cases, a dot or number will indicate pin 1 for orientation. DIPs are the most common through-hole IC. A DIP consists of 2 rows of leads, and the body is made of plastic or ceramic. DIPs usually come from the manufacturer in tubes. The tubes protect the components from ESD and lead damage and are designed to load the components into the feeders of automatic insertion machines for component placement. The most common reference designator for an IC, such as a DIP, is the letter U. The orientation marking for DIPs is either right over pin 1 or on the end where pin 1 is found. As we mentioned earlier, the most common orientation markings are a notch, a wedge, a dimple, a stripe, or the actual number, and the leads are counted counterclockwise from pin 1. IC cans are often transistors or voltage regulators. These cans have a number of long radial leads. TO5 and TO92 are among the most common sizes of IC cans. The reference designator will depend on the function of the IC can. Typical reference designators may include a U for a general IC, Q for a transistor, AR for an amplifier, or VR for a voltage regulator. IC cans contain a tab located over the highest numbered pin or between the highest numbered pin and pin 1. If you face the tab and look down at the IC can, pin 1 will be located to the right of the tab. Our last through-hole IC is the most complex. Pin grid arrays have several rows of leads extending from the bottom of the IC. The rows make up a grid of connection points. PGAs come in plastic and ceramic packages. For orientation, there is usually a notch or mark directly over pin 1. PGAs are often installed into sockets that have been soldered into the circuit board. The pin 1 location on the socket will also be marked in the same way as the PGA for proper alignment. In this section, we'll be discussing resistors, capacitors, diodes, and transistors. Resistors are a common passive component. A typical circuit board assembly will contain many resistors. The letter R is the reference designator. Resistors limit the flow of electrical current in a circuit. This resistance to the flow of current is measured in ohms. The value and tolerance of the resistor is either printed on the component or is calculated by decoding color bands into numbers. The IPC Component Identification Training and Reference Guide, IPC DRM 18, contains a color code chart for resistors and an explanation of how to read the color bands. It may be important that you understand how to decode the color bands so that you can determine the value and tolerance of a particular resistor. This way, you can be sure the correct resistor has been installed on the circuit board. Another type of resistor is called a variable resistor or potentiometer. These components may also be called trimmers or trim pots. Variable means that the value or resistance of these types of components can be changed or adjusted either by turning a shaft or sliding a contact. The maximum value is usually molded into the component body. Along with the letter R, the reference designator for variable resistors may be VAR or ADJ. Variable resistors typically have a non-symmetrical lead pattern that only allows them to be installed one way. Now let's examine capacitors. Capacitors are the most widely used component in electronics. They also have the greatest variety of shapes and sizes. The basic function of a capacitor is to store and discharge electricity. A unit of electrical capacitance is called a farad. The three most common units of measure using farads are microfarads, nanofarads, and picofarads. The picofarad has the smallest capacitance value. The value and tolerance of the capacitor is either printed on the component or is calculated by decoding color bands or coded numbers into numerical values. As with resistors, the Component Identification Training and Reference Guide contains a color code chart for capacitors and an explanation of how to read the color bands or number code. Again, it may be important that you understand how to decode the color bands and numbers so that you can determine the value and tolerance of a particular capacitor. Capacitors are either non-polarized or polarized and are designated by the letter C. Non-polarized capacitors can be installed in either direction. They are usually small and have low electrical values. They come with either axial or radial leads. Polarized capacitors also come with either axial or radial leads. The positive lead, or anode, will usually be indicated by a plus sign. This same plus sign is usually on the circuit board and will be on the assembly drawing. There may be other types of markings to identify polarity on the capacitor. There are also variable capacitors. These types of capacitors can be tuned to a particular value depending on the function required. The part number and value range is usually marked on the component. Along with the letter C, the reference designator for variable capacitors may be CVAR or CADJ. Variable capacitors often have a non-symmetrical lead pattern that only allows them to be installed in one way. Sometimes the component shape is outlined on the assembly drawing to show orientation. Now let's turn our attention to diodes. Diodes are semiconductors that allow electrical current to flow in only one direction. The reference designator for diodes is CR or D. All diodes are polarized components, meaning it is important to install them correctly. Polarity is usually indicated by a colored ring or up to 3 rings on the cathode or negative end. The diode symbol may also point to the negative end. Another type of diode is called a light-emitting diode, or LED. LEDs emit light and are typically used as display indicators on the front panels of electronic equipment. The reference designator for an LED is usually DS, although they may be identified by LED or by the diode designators CR or D. LEDs usually have radial leads. Polarity is typically indicated by the location of the cup or flag inside the lens. The cup is associated with the cathode or negative lead. In some LEDs, the negative lead will be shorter, or there may be a plus symbol on the positive side. The last component we'll be examining in this section is the transistor. Transistors are discrete components that amplify electrical signals. The reference designator for a transistor is usually the letter Q. Orientation may be accomplished by matching marked pin numbers on the transistor to pin numbers on the drawing or circuit board, by locating pin 1 to the right of the tab on a transistor can, or by matching the component shape with the outline on the circuit board or assembly drawing. Sometimes the pattern of holes on the circuit board indicates there is only one way to install the transistor. This section will examine the remaining through-hole components and connecting hardware. They include inductors, transformers and other coiled components, filters, fuses, switches, crystals, voltage regulators, thermistors, connectors, sockets, headers, and jumpers. We'll start with inductors. Inductors consist of a coil of wire that creates a magnetic field when current flows through the coil. The reference designator for an inductor is the letter L. The magnetic field produced by an inductor is measured in henries, either microhenries or millihenries. The inductor value may be either printed on the body of the component or calculated by decoding the color bars on the component's body into numbers. Again, the Component Identification Training and Reference Guide contains a color code chart for inductors and an explanation of how to read the color bands. There is no required polarity for inductors, and they usually can be installed in either direction. Closely related to inductors are transformers and other coiled components. These components also create magnetic fields. Transformers and toroids use the letter T as a reference designator. Chokes share the letter L with inductors. The part numbers and values may be marked on the component, and there's usually only one way to install them. Watch out for any coiled components that are designed without that information. Variations in wire gauge, number of turns of wire, wire spacing, internal diameters, numbers of wires, and sometimes the use of ferrite or other types of cores can change the part numbers and values. Check with your supervisor when you have trouble identifying a component. Now let's take a look at filters. The function of a filter is to allow some signals to pass and to block or filter out other signals. The reference designator for a filter is usually FL, and there is usually only one way to insert the leads into the holes of the circuit board. Fuses and circuit breakers protect a circuit from electrical overload by intentionally failing before the overload damages the circuit. A circuit breaker is a fuse that can be reset after failing. The reference designator for a fuse is the letter F. CB designates a circuit breaker. These components are measured in amps and volts. The value is usually marked on the component along with the part number. Next, we'll talk about switches and relays. Switches and relays open and close circuits. Relays are electrically operated switches. The reference designator for a switch is the letter S or SW. A relay is usually designated by the letter K. These components are measured in amps and volts and utilize a dot or notch for orientation. Our next component is a crystal. Crystals produce a consistent electrical pulse, similar to the ticking of a clock. They are available in through-hole and surface mount packages. Crystals are usually designated by the letter Y and are measured in frequency, such as kilohertz or megahertz. A chamfered corner or a dot indicates proper orientation. Now let's examine voltage regulators. Voltage regulators keep voltage constant in a circuit by minimizing peaks and valleys. The reference designator is VR, and there is usually an angle on the body or an indented dot for orientation. The last electronic component we'll discuss is the thermistor. A thermistor is a resistor that changes value based on the temperature of the component. The reference designator for a thermistor is RT. It can be inserted into the circuit board in any orientation. Let's complete this section by discussing connecting hardware. This hardware is available in both through-hole and surface mount package styles. Connectors are attached to a circuit board so that wires, cables, and other outside connections can be made to the assembly. The reference designator for a connector is the letter P. Connectors also use the letter J as a reference designator. Connectors are oriented based upon a bevel, notch, or pin number molded into the package. Another type of connecting hardware is a socket. Sockets are soldered onto a circuit board so that an IC or PGA can be plugged into the socket without being soldered. This makes it easier to remove and replace a component that might be upgraded or changed in the future. The reference designator for a socket is some variation of the letter X. Sockets usually have a notch or dot to indicate orientation. The component being plugged into the socket will have an identical orientation marking. The next type of connecting hardware we'll discuss is the header. Like connectors, they are used for outside connections. Headers don't usually have a housing around their pins. They also use the letter J or P as a reference designator. Headers usually have alignment or locking tabs for the connector, which mates with it. The last type of connecting hardware we'll examine is the jumper. Jumpers connect two pins on an assembly together, providing an electrical path between those points. The reference designator for a jumper is W or E when the jumper is a wire, and the letter P when the jumper is a plug. Surface mount components are designed so they can be placed directly onto lands on the circuit board, as opposed to being inserted through mounting holes in the board. They have the same types of electronic functions as the comparable through-hole components. Many through-hole components have surface mount equivalents that are much smaller in size. What this means is that considerably more electronic functions can be present in a surface mount component that is the same size as a through-hole component. Surface mount devices use the same system of part numbers, reference designators, and component values and tolerances as through-hole components. And the indicators for polarity and pin 1 orientation are also similar. What's different is that surface mount assembly is more compatible with automated processes than through-hole assembly. Because of their size and shape, many types of through-hole components require manual insertion. Almost all surface mount components can be placed by machine. The components come packaged from the manufacturer in one of 3 forms: on tape and reel, in tubes, or in waffle trays. Let's take a look at how each of these methods of packaging is loaded onto a placement machine. Notice how the operator checks the part number on the reel against the bill of materials. That's because these components are too small to have part numbers marked on them. This operator is making sure component polarity is correctly oriented before loading these tubes into the feeders. It's also important to check pin 1 orientation when loading component trays. Another difference is that surface mount components don't have long leads. That's because they don't attach to holes through the circuit board. Instead, they attach to the lands on the surface of the board with either special leads or leadless terminations. We'll talk about leaded components first. Surface mount components have 4 styles of leads: gull wings, J leads, L leads, and I leads. Gull wings and J leads are the most common. The gull wing lead is a metal lead that bends down and away, similar to a seagull's wing. Some gull wing components are said to have fine pitch. Pitch is the distance between the center of one lead to the center of the next. Fine pitch means that the leads are spaced very close together. J leads have metal leads that bend down and underneath the component in the shape of the letter J. L leads are found on molded tantalum capacitors and are formed inward, almost touching the body of the component. I leads are actually through-hole leads that have been cut short for surface mounting. The end of the modified lead is placed directly on the surface land. As you can imagine, this connection won't be as strong or stable as the other types of surface mount leads, and IPC standards do not permit their use on high reliability products. Next, let's take a look at the leadless types of surface mount connections. Leadless means there are no metal leads sticking out of the component body. Instead, the components are attached to the circuit board by soldering to some type of metallized termination on the component. The most common type of metallized termination component is the chip component, with 3 or 5-sided terminations at opposite ends of the component's body. Castellations are another form of leadless connection. These half-round metallized recesses in the side of the component are filled with solder when connected to the circuit board land. In addition, there are no lead components. These packages come in 2 styles: dual flat no lead, or DFN, and quad flat no lead, or QFN. Both DFNs and QFNs have terminal pads underneath the component that are soldered directly onto circuit board lands. The last type of leadless connection is the array type component. Ball grid arrays, or BGAs, consist of parallel rows of tiny balls of solder on the bottom of the component. These solder balls are connected to matching rows of lands on the circuit board. There are also ceramic column grid arrays, or CCGAs, that connect to matching lands on the circuit board. Another array type component is the land grid array, or LGA, that has a series of flat land terminations that are soldered directly to matching circuit board lands. In this section, we'll be examining the surface mount ICs. We'll start with the large-scale ICs. The larger scale ICs usually come from the manufacturer in waffle trays. These complex components may be packaged in several package styles. The 2 most popular of these styles are quad flat packs, or QFPs, and plastic leaded chip carriers, or PLCCs. The body of a QFP is usually plastic. Their component bodies can also be ceramic or metal. QFPs have gull wing leads on all 4 sides. They can have anywhere from a few to hundreds of leads. The body of the component is usually marked with a part number, date code, place of manufacture, and the logo of the manufacturer. The reference designator for QFPs, like all other surface mount and through-hole ICs, is also indicated by the letter U. Orientation for QFPs is indicated by a dot or a beveled edge over the number 1 lead. Sometimes there may be a chamfered corner or a stripe for pin 1 orientation. Now let's look at PLCCs. PLCCs are also a popular large-scale IC package style. They can have up to 100 J leads on each of the 4 sides. Notice that J leads are not spaced as closely together as the gull wing leads on fine-pitch QFPs. Orientation markings for PLCCs are not the same as for QFPs. A center dot indicates pin 1. Next, let's discuss some of the large-scale leadless ICs. These include leadless chip carriers, or LCCs, QFNs, and the array-style components, BGAs, CCGAs, and LGAs. LCCs are most commonly used in aerospace applications because they are extremely rugged. Smaller, hybrid varieties are currently being designed and used for military and telecommunications applications. As we mentioned earlier, LCCs utilize half-round metallized recesses in the side of the component called castellations. There can be up to 124 castellations on the larger LCCs. Like the leads on ICs, castellations are counted counterclockwise from the pin 1 orientation mark. The QFN is a cousin to the QFP. Instead of having gull wing leads that extend out from the component, the QFN contains perimeter lands on the bottom that connect to the corresponding lands on the circuit board. The bottom of the package also contains an exposed thermal pad that improves heat transfer from the IC to the circuit board. QFNs can have a single row of lands or multiple rows of lands. These lands are counted counterclockwise from the number 1 pad, starting with the row on the component edge. The other large-scale leadless ICs are the array-style components. We'll start with the BGA. Instead of leads, the BGA contains from 25 to 625 or more tiny solder balls on the bottom of the component. These solder balls connect to a matching set of lands on the circuit board. The body of the BGA may be made of plastic, ceramic, or metal. BGAs utilize the same orientation markings as the other large-scale ICs. A cousin to the BGA is the CCGA. As stated earlier, CCGAs have solderable columns instead of the tiny solder balls to connect to the matching lands on the circuit board. CCGA packages are becoming increasingly popular as an alternative to ceramic BGA packages for applications requiring very high-density interconnections with higher board-level reliability. The last type of array-style component we'll mention is the land grid array, or LGA. For identification purposes, an LGA is simply a ceramic BGA or CCGA without the balls or columns. They are simply a series of flat pads or lands that are soldered to corresponding lands on the circuit board. At this point, let's take a look at the smaller scale ICs. These undersized packages with leads on 2 sides are called Small Outline Integrated Circuits, or SOICs. SOICs are the surface mount equivalents of through-hole dips. These components come from the manufacturer in tubes, or on tape and reel. SOIC bodies are typically plastic and have gull wing leads. When these components have J leads, they are called SOJs. Like the larger scale surface mount ICs, orientation is indicated by a dot or beveled edge over the number 1 lead, or by an end notch or stripe on the body of the component. Other styles of SOICs are all gull wing leaded components that usually begin with the letters SO for small outline. The remaining letters indicate the size of the component package, the composition, P for plastic or C for ceramic, or to the thickness of the body, where T refers to thin packages. A leadless cousin to the SOIC is the DFN. DFNs are smaller versions of QFNs since they have 2 rows of terminal pads rather than 4. The bottom of the package also contains an exposed thermal pad that improves heat transfer from the IC to the circuit board. The lands are counted counterclockwise from the number 1 terminal pad. In this last section, we'll be discussing chip components, MELFs, transistors, and diodes. We'll start with chip components. Chip components usually have ceramic bodies with metallized terminations on either end. The most common types are chip resistors and chip capacitors. Inductors have recently been introduced in this package style. These components come from the manufacturer on tape and reel. Chip components are typically placed on circuit boards using high-speed chip shooters. Because the components are so small, there's often no identification marking on the body. This makes reading the value of the component impossible. That's why it's critical that the part number on the reel is verified against the bill of materials, and that the feeder containing the reel of components is loaded into the correct feeder location on the chip shooter. Like their through-hole counterparts, chip resistors use the letter R as a reference designator, and chip capacitors use the letter C. Chip resistors and capacitors may have numerical value and tolerance codes rather than color codes. These codes are sometimes printed on the component body if the component is large enough. More often, the value and tolerance is printed on the label of the tape reel along with the part number. The Component ID Reference Manual contains an explanation of how to read the number codes for resistors and capacitors. Another type of chip capacitor is the molded tantalum capacitor. This type of capacitor has inward-formed L leads that look like metallized terminations. Molded tantalum capacitors are polarized. Polarity is indicated on the positive or anode end by a line, a plus sign, or the letter A. The top of the component may also be beveled on the anode end. The physical size of the molded tantalum capacitor is described by one of 4 letters: A, B, C, or D. A is the smallest and D is the largest. Next, let's examine MELFs. MELF stands for Metal Electrode Leadless Face and comes in a round package. MELFs have metallized terminations on each end of a cylindrical body. MELF components include resistors, capacitors, diodes, and inductors. Like chip components, MELFs usually come from the manufacturer on tape and reel. The label on the reel will usually display the part number. Reference designators, value coding, and polarity indicators are pretty much the same for MELFs as for their surface mount chip and through-hole counterparts. For example, the color band system for specifying values and tolerances of MELF resistors, capacitors, and inductors is the same system that we used for through-hole components. Polarity is indicated on MELF diodes by a band on the negative or cathode end. The last surface mount package styles we'll discuss are small and large transistors and diodes. Small outline transistors, or SOTs, are small rectangular transistor or diode packages. SOTs usually have 3 or 4 gull wing leads on 2 sides of the package. SOTs come in different sizes. The most popular SOT is the SOT23. As with any transistor or diode, the reference designator is Q for transistors and D or CR for diodes. Orientation of SOTs is determined by the lead and land patterns. There is only one way to place the component. Diode packages, or DPACs, accommodate more complex groups of transistors or diodes. DPACs have 3 gull wing leads. Like SOTs, they can only be placed on the board in one orientation. Both SOTs and DPACs have equivalent through-hole transistors and diodes. This program has presented many of the most important details of component identification. First, you were introduced to through-hole components and surface mount components, and took a look at the relationship between the component, the circuit board, the assembly drawing and bill of materials, and component reference designators. We also discussed component values and tolerances, polarity, and orientation. Then we continued with the identification of through-hole components. We covered ICs, common axial and radial components, and the remaining types of through-hole components and connecting hardware. Next, we discussed the differences between through-hole and surface mount components. Then, we identified the surface mount components. First, we looked at the larger scale leaded and leadless ICs. Next, we examined the small outline ICs. And we concluded with a discussion of chip components, MELFs, SOTs, and DPACs. Identifying components correctly is one of the most critical jobs in electronics assembly. Improper component ID can result in damage to the component and circuit board. It's important to understand part numbers and CRDs, along with component values and tolerances. And you need to be able to verify polarity and pin 1 orientation. Careful attention to detail will help to make sure that your company's products work properly and reliably. The more knowledge you have, the better you can do your job.